we will do design of various type of slabs using user-friendly software. This is table 37 given in SP16. Number of tables are given in SP16 where you can find the spacing of particular bar required for a known moment of resistance. Okay, in this table we can see some in this region the values are written as 0 because in this region the slab is found to be over reinforced. Okay, so we are taking table 37 where FCK is 20, F5 is 415 and the thickness of slab is 12 centimeter, that is 120 mm. Okay, using of this table is very cumbersome. Okay, because most probably our moments fall in between and then we have to do the interpolation. Even the spacing is found to be in between some of these two values, and again we have to do the interpolation, right? So in that case we can do the graphical representation of this value, and the graphical representation is something like that, right? So we can see there are three graphs drawn over here. Black graph represents when 8 mm dia bar is used as main steel. Red graph represents when 12 mm dia bar is used as main steel. Green graph represents for the 12 mm dia bar used as main steel. Okay, so a question comes in our mind that why bars of dia 16 and 20 mm are not shown over here. Okay, because the code has given a restriction that you cannot use a bar diameter larger than d by 8, where d is 120 mm, right? So when the thickness is 12 centimeter, or you can say what 120 mm, you cannot use bar diameter larger than 12 mm. Okay, so this is the graphical representation of the above values. So let us start with an explanation. Say suppose we are going to use 12 mm dia bars as main steel, then when the spacing is kept to be 120, then the corresponding moment of resistance is found to be 27, and the EST required per meter is 941.66. Okay, so this is spacing 120 and corresponding moment moment of resistance is 27, right? We can see this in the table. 12 mm dia bar, 120 mm spacing, this is centimeter, I am telling 120 mm, so 12 centimeter. Okay, the moment of resistance is 26.99. okay, this is 27, right? Say now you are going to use 10 mm dia bar as your main steel and the spacing is 100 mm, then the corresponding moment is 23.75, right? And the EST required per meter is 782.55, right? So this is shown over here. Okay, let us see the table. 10 mm, 100 mm spacing, and the moment of resistance is 23.7, right? Similarly, for 8 mm, say when the spacing is 60 mm, then the corresponding moment is 25.5, and so on, right? So this is the screenshot of the program where we have taken the same values: D120, clear cover 15, F5415, FCK 20. Okay, SP16 has been developed with an assumption that the clear cover is 15 or the diameter of bar, okay, whichever is larger. Okay, in our case the largest diameter bar is 12 mm, so the clear cover that is to be taken is 15 mm. Okay, so we can run this program in the software. Okay, let us go to design section, program list. Okay, this is the program. We will draw the graph. Okay, right, D we know is 120. Okay, very important. This note is very important. Somewhere it is written you have to press tab key, somewhere it is written you have to press enter key. So you have to follow this strictly, then only the data given in the text box will be saved, right? Over here it is tab key, so press tab. Okay, clear cover 15, press tab. F5 415, press tab. FCK 20, right? So these are the three graphs which we saw in the screenshot. Okay, so if you want to use 8 mm bar, just select this option and scroll the pointer on the black graph, because this is for sorry, black graph represents when the 8 dia bar is used as main steel. Okay, bring the pointer exactly on the graph. Okay, and you say when your mu is 11.25, then the spacing required is 154, ast required is 325. Below you can see the minimum ast required is 144. So provided 325 is greater than 144, is okay. Spacing is 154. Okay, and maximum allowable spacing is 291. So the provided or required spacing is less than allowable, so it's okay, fine, right? Similarly, so you don't have to do interpolation. That's a big relief. Okay, so say if you want to use 10 mm diameter, click this option, bring the pointer on the red graph. Okay, and now say if the moment is 14.25, then the required spacing is 180 and the steel required per meter is 433 and so on, right? So it becomes very easy. You can do the design of slab in few seconds, right? So once you have found the steel, then you have to do the calculation for one base shear. Over here, for when we are using 10 mm dia bar, the spacing required per 1 meter is 433 mm. Please remember that. So click this. Okay, say shortest span is 5 meters, press tab. W is say 15, press tab. And steel was 433. Okay, then calculate. Okay, so the permissible shear stress tau C is found to be 0.58, and actual nominal shear stress is found to be 0.36, which is less than tau C, so it's okay. So this is how you can do the design of any slab, whether it is one way or a two way. Okay, because this program is related with the moments and the corresponding spacing in steel. Okay, this program does not find the moments. Okay, it just finds the spacing and the steel required per meter, right? So this has nothing to do with it is whether it is one way or whether it is a two way. Okay, now this is for a two-way slab. Okay, if it is a simply supported two-way slab, use this option. This is a graphical representation of the coefficient given in the code. These are the coefficients. Say if your W is 15, press tab. Lx is 5, press tab. Ly is 6, press tab. Okay, calculate. So these are the moments for which you have to find the steel, right? If you have a restrained slab, okay, and the condition is second, that is one short and discontinuous, click that option, click the restrained slab. So this is a graphical representation. These are the coefficients. Give W over here, say 15. Okay, press tab. Lx is 5, Ly is 6, calculate moment. Okay, so this gives the moment, that is mx positive and mx negative, my positive, my negative. Okay, so once you know this moment, you can go to this program and find the required steel, right? So this makes your work very easy. Okay, fine. So this is what we tried to understand over here, that this values can be shown graphically like this, right? And we can just get the values by scrolling the pointer on the graph, right? Fine. Now in practical field, we have multiple slabs to be designed together, right? These are the slabs for one flat. This is one flat and we have another flat on this side. Okay, so I'm not shown because it is typical, it's a mirror image. So we will design all the slabs of this flat in one stroke. Okay, after that we will do the design of this staircase, right? So this is the table showing the details of all the slabs. These are slab numbers, shows type of slab, whether it is two way or one way. These are types of panel as according to table 26 IS 456 2000. Lx, Ly, total factor load, overall depth D. Some overall depth D has to be assumed because we have to find the sulfate, right? And this is FCK, right? So we will design all this slab in a single stroke with the use of software. Okay, so for that we will use this software. Okay, right. These are the 9 conditions of the restraint slabs given in the code IS 456 2000. Sorry, this is condition 10, that is for one way slab. Okay, so over here, please first the very first thing is that you have to read this node. Okay, over here we have to press enter to save the data written in the text box, right? So fck is 20. Okay, so let us give the data. fck 20, press enter. F5 is 415, press enter. Okay, so for first slab, the longest span is 9 meter, press tab. Shortest span is 4.5 meters, press tab. Load, effective load is 13 kilonewton meter square, press tab. Condition is 2, press tab. Thickness we have assumed is 165. Okay, if the thickness is found to be inadequate, then the program will take a higher thickness by itself, right? Press enter. So now we can see, as all the data is written over here, that means the all the data has been saved, right? Now let us give the data for the second slab. Okay, it is 4. It is 4.5, press enter. 4, press enter. 12.5, press enter. 4, press enter. 150, press enter. Okay, fine. Let us give the values for the third slab. 6, press enter. 5, press enter. 13.5, press enter. 8, press enter. 175, press enter. Right? Now fourth slab, right? 6, press enter. 5, press enter. 13.5, press enter. 8, press enter. 175, press enter. Right? Now let's take the fifth slab. That is 5, press enter. 4, press enter. 12.5, 8, 150. Okay. Now sixth slab. 4, 3.5, 12, 4, and 135. Okay, then seventh slab, it is 5.5, 3, 11.25. Okay, 0.25, 11.25. Just a minute. Okay, 11.25. Okay, press enter. Condition is, okay, condition is 4. Okay, press enter. And sorry, condition is 4. Okay, right, perfect. And thickness is 120. Press enter. Right, now let us give for 8th slab 2, 10.5, 10.5. Okay, 2 and 100. Okay, then for 9th slab 2.75, 2, 10.5, 2 and 100. Okay, for 10th slab 9, 1.5, 10.5, 10, 100. Okay, for 11th slab it is 3, 2, 11, 9, 115. Okay, so this is how we have given the data for all the 11 slabs, right? Fine. So just click finish. Okay, so here it is asking, are there any further editing to be done? So if by mistake you have given some value by wrong, if you have given some wrong values, then you can edit it. Just click no. Edit button will be populated. Write the number of members, say 4. Okay, press enter. So you can edit the value over here. Okay, edit the value and press enter, and just move out, right? And the value will be changed over here, right? Okay, now click finish. Okay, no editing is to be done, so yes, right? Okay, let's see the output. So this is how we designed all the 11 slab at one stroke, right? Okay, fine. So this is slab number 1. This is mx negative, this is mx positive, this is m by negative, this is m by positive. This is still required for this moment, this is still required for this moment, this is still required for this moment, this is still required for this moment. Okay, and this still should not be less than EST minimum, which is displayed over here. Okay, so this is how we get the moments still in this output. We can also get the chart of this. Okay, so this is chart, right? So over here we directly get the spacings required that is to be provided, right? This is depth in mm, this is main steel spacing, this is spacing in the other direction, that is this is along lx, this is along ly, right? So this bot means bottom steel, that is this is main steel, so along lx, right? So this is ASTX positive. Okay, this is ASTY positive, right? And top steel, so it is negative steel, right? So this is ASTX negative and this is ASTY negative, right? So if you are going to use 8 mm dia bar, then the spacing required is 171. If you are using 10 mm dia bar, the spacing required is 266. If you are using 12 mm dia bar, the spacing required is 382, and so on. Similarly, in along ly. Okay, so this is how the spacing has been displayed over here, required spacing, and the code says for main steel the spacing should not be less than 3 times the d effective depth d, or 300. Over here it is 300 because 3 times the d is found to be greater than 300. So we have to take the least of these two, so that is 300, right? So if your spacing is found to be greater than 300, then you have to take 300. Okay, if it is a distribution steel, then it will be 5 times the d, or 450. Over here 450 is found to be lesser than 5 times a d. Okay? So this is how the whole table has been shown over here. So you can directly get the value of spacings and give the detail for execution, right? Fine. So this is how I have shown over here. This is the screenshot of the uh, design of all the 11 slabs, which shows the moments and the steel, that is slab 1 2 3, slab 4 5 6, slab 7 8 9, and slab 10 and 11, right? And this is the chart which we just saw. This is screenshot of the chart, okay, which we just saw in the software now, right? Okay, now the next step is we have to distribute the load from slab to the beam. Okay, so this shows the equivalent loading passed on from the slab to the short edge beam and the long edge beam, right? So for that it's very simple. Okay, this is the assumption made by the code, okay, that how the load will be distributed to the beams. Okay, so we will distribute the load from the slab to the beams in this manner. Okay, simple. You just have to click this program. This asks whether have you executed the slab rectangular slab program. Yes, we have executed. So write OK, click OK, and we can see the output. Okay, so this is the output. Okay, so load going on the short beam is 19.5 and load going on the longer beam is 26.81 for slab 1. So let us see slab 1. Okay, this is slab 1. Right, this is slab 1, right? So load going on the longer beam is 26.81 and load going on the shorter beam is 19.5. Okay, so this is how we get the load distribution on the one click. Okay, so this is the table, screenshot of the table which we just saw in the software now, that is load distribution, right? Okay, so this is how we designed all the slabs. Now we want to design the staircase, right? Now we can see the dimensions of the staircase are so. Okay, this is landing 1. The length of landing 1 is 2 meters. This is the horizontal projection of the steps is known as total going, and that is 3 meters. This is landing 2 and the length of landing 2 is 1.2 meters. Okay, so we want to now design the staircase. Very simple. It takes hardly a minute when you design it with the software. Okay, so let us move to the section staircase. Okay, we have to assume the depth of the staircase, say it is 250. Okay, this is 250, so this d is going to be 279.5. Okay, you can calculate the self fit using these steps. The factored dead load on going is found to be 14.25. and factored dead load on landing is found to be 10.5. Factored live load is found to be 4.5. So this is dead load plus live load, this is 15. Dead load plus live load, this is equal to 18.925, and this is again 15. This is landing 1, this is going, this is landing 2. Okay, so what we will do, this is one single member, but we will create two imaginary nodes, node 1 and node 2, because the magnitude of the UDL is changing over here, right? So we will get moment over here, 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 and here from the analysis, which is shown over here. Okay, so let us do the analysis of this. Okay, so let us move to the analysis part. Okay, we'll do 2D analysis, right? Okay, first select the scale. Let us take 1:10. Okay, now first of all, okay, please remember you have to use enter key to save all the values, right, in the given in the textbook, right? So the first we have to draw the landing, horizontal projection of the landing. Okay, the length of the landing is 2 meters, so it will be 0. We will go, we are giving the coordinates, right? Press enter, 0, press enter, 2, press enter, 0, press enter. Okay, so this is first landing 1 drawn. Now we want to draw the horizontal projection of the total going, right? So the length of the total going is 3 meters. So this will be 2, press enter, 0, press enter, 5, press enter, 0, press enter. Okay, so this is how we draw the going. Now we want to draw the landing 2. The length of the landing 2 is 1.2 meters, so it will be 5, press enter, 0, press enter, 6.2, press enter, 0, press enter. Okay, now over here we have, this is our node 1, this is our node 2. So joints are to be numbered first. Just click, the number will be populated by its own. These are supports, click over here, click over here, right? So joints are to be numbered first and supports are to be numbered last, which is explained over here. Okay, so joints are to be numbered first and supports are to be numbered at last. Okay, right. Okay, is the drawing complete? Yes. Have you filled the text box? Yes. Okay, write the total number of joints 1 and 2. Okay, so 2, press enter. Write the total number of supports 1 and 2, so 2, press enter. So support number 3 is simply supported, so we'll take hinge. Okay, support number 4 is simply supported, so we'll take hinge. Okay, so this has changed to green. Okay, because they are taken as simply supported. Now we have to select the option for giving the data. For continuous beam we have to select manual, so okay, select manual. Okay, close this text box and press enter. Okay, and press enter. Okay, okay, so do you want to select this member? Yes. Okay, fill the property. Okay, so this is a design of staircase, so we design 1 meter strip, so width will be 1 meter, press enter. Depth is 0.25, that is 250 mm, press enter. We are giving the data for this part, right? So the loading on this landing 1 is 15 kilonewton per meter square, so 15, press enter, enter. No other load is there, so just move out of the form. Okay, now do you want to select this member? Yes, say yes. Okay, fill the property table. Okay, width is again 1 meter, depth is 0.25 meters, loading on going is 18.925 kilonewton per meter square. Okay, 18.925. Okay, so just press enter and move outside. Okay, okay, now third member, this is landing 2. Okay, we will fill the property for that. Width is 1 meter. Okay, press enter, 0.25 is depth and the loading is 15 kilonewton per meter square. Press enter, enter and move out. Okay, now let's save the file. Okay, let us save it as staircase. Okay, stair you can say. Okay, let us save it. Now we can do the analysis, create input. Okay, run analysis. Okay, our FCK is 25, so E will be 25 1 2 3 4 5 6. Okay, fine. Now we have to give the load factor. We have already provided factored loads on the staircase, so we will write 1 over here. Okay, 1, press enter, press 1, press enter, right? If we had given the working loads on staircase in the detail or in the table sheet, then we would have to write 1.5 and 1.5 over here, right? But we have already given the factor load, so we are writing 1 and 1 over here. So please click OK, and let us click finish. Okay. Okay, so we can see the output. So this is the output, right? Fine. You can see the bending moment. You can see the shear force. Okay, you can see the individual bending moment and shear force. We want to find the bending moment shear force for this member number 2. Write 2 over here, press enter. You can see the shear force, you can see the bending moment at the starting point over here, right? And shear force at the starting point over here. You want to see the bending moment and shear force over here, then just like this. Or you want to see the bending moment shear force at some particular distance, right over here, and press enter, and you get the shear force and bending moment at that particular point, right? So this is how we we can see the shear force and bending moment, right? This is of not use right now, because this all calculation will be done by the program staircase, right? So we will move further. Okay, let's go to design section. Okay, program list, with slabs staircase, right? Okay, after doing the analysis, we directly have to come over here. Okay, F5 is 415. Okay, please use enter key. Okay, please use enter. FCK is 25, press enter. Okay, if the thickness is to be thickness of depth of the slab is to be restricted, yes, of course we have restricted it to 250. So we will write 1, and depth is 250 mm. So press enter, right? Now okay, finish. You can see the output. Okay, so this is the design of the slab staircase. We can see, I have seen this is a screenshot which we got just now, obtained from the software, right? So this is member number 1, right? This is member number 1. Design at left is 0, moment at left is 0, moment at right is 73. This is the corresponding steel. You have to provide 50% of this steel over here. Okay, and this should not be less than the minimum steel, okay, which is not, so it is taken 50%. Okay, this is member number 2. The maximum design moment is 85, so maximum moment is 85, and the corresponding steel is shown over here. This is AST per meter. Then moment at left 73.26, moment at right 52, corresponding steel are shown over here. This is member number 3. Then moment at left is 52, moment at right is 0, corresponding steel are shown over here, and over here 50% of this steel is shown over here, right? So this is how the program does a lot of work for you. You just have to now select the perfect diameter of the bar, and just give the spacing as according to the diameter of the bar selected, right? Fine. So this is what we did the design for an simply supported waist slab staircase, right? Say suppose we want to design this staircase as a thread riser staircase, right? Simple, everything remains the same. Okay, so now we will take the thickness of thread riser slab staircase as 150 mm. Okay, assume the total depth of the thread riser step is equal to 150 mm. T is 300, R is 150. So only thing is that the thickness has changed and the loading will be changed. Okay, now the loading will be reduced. Okay, total factor load ongoing is 14.1. and total factor load on landing is 11.25, right? 11.25, 14.1, 11.25, everything remains the same. Thickness changes, right? First the loading was 415, 18.925 and 15, right? Now it is 11.25, 14.1 and 11.25. Okay, so nothing has to be changed. We will just open that file again. Okay, and we will change the loading existing file. We will open stair, open. Okay, edit data. We'll edit data for member number 1. Yes. Okay, so this is changed to 0.15, right? 150 mm. Press enter. Okay, loading is changed to 11.25, right? Press enter and move outside. Okay, okay, for second member number 2. Okay, so this has changed to 0.15. Okay, and this loading has changed to 14.1. Okay, press enter and move outside. Okay, now member number 3, this has changed to 0.15, and this has changed to 11.25. Press enter and move outside. Okay, let us resave the frame. Save, right? So it's in 2D frame, so we'll click this yes and run the analysis. Run input. Okay, run analysis. We know our E is 2500000. Press enter. Load factors to be given are 1 and 1. 1, press enter. 1, press enter. Okay, okay, finish, and we'll wait. Now you can see the output. Okay, this is the output. Okay, we'll directly go to the staircase section. Okay, program list, west slab staircase. Okay, F5 is 415. Press enter. F6 is 25. Press enter. 1, yes, 150. Press enter. Okay, finish. You can see the output, right? So this is, I have taken the screenshot of this over here, right? This is a screenshot. Okay, for this. Okay, so same for the required moments. This is the moment. Okay, over here moment is 0. Over here the moment is 54.7. Over here the moment is 39.554. Over the moment is 0, and the maximum moment is 63.89. so the steel is calculated over here. Okay, detail, the steel in detail has been calculated here over here. So you just need to choose the diameter bar and give the appropriate spacing, right? So now we'll take another type of staircase, that is example 12.6, page 600, reinforced concrete design by S.U. Pillai and Dr. Devdas Menon sir. When the slab, when the staircase is supported on its side, right? So in such cases we will have two systems. One is, this is system 1. Okay, you have to take the center of the landing. Okay, and this will act as one system, and the load of this will come on the landing, and this landing will span in this direction, and then you will have to design your landing, right? So this first system, in this first system, this turns out this is 1.25. So half of that is 0.625. If this was found to be greater than 1 meter, then this cannot be greater than 1 meter, right? You have to take it as 1. But this is found to be 0.625. This is found to be 0.625. So we'll take this as 0.625. That's the length of landing 1. Length of going will be 2.43, and length of landing 2 will be 0.625, right? Fine. So these are the loadings on it. Okay, as this landing is common to system 1, and system 2. Okay, so the loading over here to be taken will be half of the actual. Okay, so actual loading on the landing is 15.35 kilonewton per meter square. Okay, so we'll take half of that, and that is equal to 7.68 kilonewton per meter square, right? So this, for this loading we get this moments, and for this moment we get this result, that is the steel required for the design. Okay, simple, very simple. So I have explained this in detail, so I'm not going again in depth. Okay, and after that, this is the loading from the going half. This is total going area, right? So 2.43 is the length into the load, kilonewton per meter square is 19.47. That gives the total loading divided by 2. Half the loading will come over here, half the loading will go over there. So that is equal to 23.66 kilonewton per meter. Okay. Now direct loading on the landing is 15.35 kilonewton meter square into this width is 19.19 kilonewton per meter, right? So now we are going to design 1 meter strip. So this plus this divided by 1.25 is the width. So this gives 34.28, that is this W. So for this W, you find WL square by 8 moment, that is 29, and you find AST. That's very simple. So you can design the staircase in this manner. Okay. Now say if we wanted to design this staircase as thread riser staircase, then simple, we just have to give this input. Fy is 415, fck is 20, length of landing 1 is 1.2, right? Length of going is 2.43, length of landing 2 is again 1.25, that is 1.25. Okay, so these are the factored loads which are given in the reference example. Height is also given in the reference example, 160 height of riser, and thickness is of the thread riser slab is also given in the reference example as 145, and width of the landing. Now landing is spanning in this direction. Total width is 2.6. Okay, so 2.6. So this is the data which we will give, and we will get the required steel for the folded staircase, right? So let us run the program. Folded staircase. Okay, right? So this is our option. Side edge is supported, right? So click this option. Okay, and give the values. Over here it is written that you have to press enter key. Okay, to give the to save the values. Fy is 415, press enter. Fck is 20, press enter. Length of landing 1 is 1.25 meters, press enter. Length of going is 2.43, press enter. Length of landing 2 is 1.25 meters, press enter. Factored load on landing is 14.97. Okay, press enter. Factored load on going is found to be 17. It is 17.06. Okay, height of riser is given in the reference example as 160. Okay, thickness is given as 145 in the reference example. Width of landing is 2.6. Press enter. Okay, please don't forget to press enter even after the last values filled in the text box. Okay, finish, right? So we get the total main steel. This is the main steel. Okay, in thread riser unit. Okay, that is in the going portion. Distribution steel, these are the distribution steel. That area is equal to this much. In landing, the main steel is going to be this, right? All these round dots are going to be main steel, right? That area per meter required is equal to this much. Okay, and the thickness as in 145 is found to be okay. So you can design all different type of staircase in just a single minute. Okay, so this is how it is very good to use user-friendly software which can save your time, energy, and avoid long calculations, right? Fine. So this is how we design the different various type of slabs in a floor, and different type of staircase with possibility of staircase which can be provided in that flat, right? Okay, now we will come to a flat slab. Okay, design of flat slab by direct design method. We will take example 3.1, chapter 3, flat slab reinforced concrete volume 2 by Dr. H.J. Sasser, page 43. So this is a typical equivalent frame. Okay, there are four, you can say four spans: span 1, span 2, span 3, span 4. All are of 6 meters. This is exterior span, this is exterior span, this is interior span, this is interior span. Okay, the thickness of flat slab assumed is 200 mm, and no drops and no column capitals are to be provided, and we will design the interior span. Okay, so the width of the equivalent frame is 4.5 meters. Okay, and the size of the column above the flat slab, all the columns are of size 300 by 400. Even below the flat slab, all the size of the column is 300 by 400, right? Okay, over here we can see this color shows half meter strip. This is half meter strip. This is half meter strip for this equivalent frame. This is half meter strip. This is half meter strip for this equivalent frame. This is column strip. This is column strip. So these two half meter strip together form a middle strip which is bounded on each side with the column strip, right? So now we will move forward. Okay, so there are four spans: 1, 2, 3, and 4. Each span is of 6 meters. Okay, so we will give the input data in the software in the same manner, right? Okay, given to us Fy is 4.5, Fck is 20. These are the size of widths which I obtained from the software, and also are obtained from the reference example. Column width is found to be 2.25 meters. Half middle strip is 1.125 meters. Total middle strip is into 2, that is 2.25, right? This is 1.125, this is 1.125, this together will be 2.25. Okay, fine. An important note I have made over here, that according to clause 31.4.5.2, page 55, IS 456-2000, an interior support, the supporting member above and below, that are column, the supporting members are column, right? Above and below the slab shall be designed to resist the moment M equal to this one. Okay, what does this mean? You will have a moment over here, you will have a moment over here. So subtracting this moment from this moment, you will get the unbalanced moment, which has to be transferred to the column. Okay, that unbalanced moment should be greater than or at least equal to this much. Okay, so over here Ln is the clear span of the considered span, and Ln dash is the clear span of the shortest span. Okay, but this in the software, Ln dash, in our case Ln and Ln dash are same because all the spans are same, but in software Ln dash is taken as 30% lesser than Ln, which will give us more additional punching shear stress and slightly give a conservative result in case of a punching shear. Okay, but the moments which are found by the reference example and that are found by the software has to be the same. Okay, so overall depth is 200, effective depth is 180 for the example. Okay, the program takes effective depth as 150. Okay, as the effective depth varies, so the steel will vary. Okay, the steel area will vary, but the moments will remain the same. Okay, self weight is taken as 5, finished load is taken as 1, live load is taken as 4. These are all working loads. Okay, so these are the output from the reference example, and we will compare that with the software, right? So let us run the software. This is the result of the software, screenshot taken from the software, right? So we will run this flat slab program DDM. Okay, so we have 4 spans, 1, 2, 3, and 4. Okay, so write the total number of span is 4. Okay, please read this. You have to press enter key. Okay, don't forget this. Okay, so let us write 4, press enter. Okay, so member 1, span 1, length of all the spans are of 6 meters, so we will write 6, press enter. 6, enter, 6, enter, 6, enter, right? Now joint 1. Coming to the joint 1. Okay, we have to give the width and depth of the column. BU means above the slab, and BB and DB means the width and depth of column below the slab at that joint. Okay, but we know all the column, that whether it is at top, above the slab or below the slab, all the width and depth of the column are 300 by 400. So we will give all the width 300 and depth 400. Okay, so 300, press enter, 400, press enter, 300 is the width and 400 is the depth. Okay, this is width and depth of column above the slab. This is width and depth of column below the slab at joint 1. Okay, press enter, right? Similarly, we have to repeat the same size. Okay, 300, press enter, 400, press enter, 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 300, press enter, 400, press enter. And the last fifth joint also, size of the column remains the same. 300, press enter, 400, press enter, 300, press enter, 400, press enter. Okay, now L2, the width of the equivalent frame is 4.5 meters. Okay, F5 is 415, FCK is 20, height of story is 4. Okay, wide. Now the depth of slab, this is the depth of slab that can be assumed, but in example it has been taken as 200, so we will take 200. Okay, 200 mm. Now you have to press tab, right? Over here it is written use tab. Okay, now depth of drop slab, there is no drop slab, but the depth of the slab surrounding the column is 200, so we will delete this and write 200. Okay, press tab. There are no drops. Okay, so we'll give the width and length of the drop is equal to 0, and there are no capitals, right? So again this will be 0. Okay, working live load is 4. Okay, and now we have to just click finish. Okay, the total dead load, that is finished load, working load is 1. Press enter. Simple. The complete design of flat slab has been completed, right? So easy, it just took 1 minute, right? So the screenshot of this has been shown over here. Okay, now we have to see the interior panel. This is interior panel. Okay, so this is span 2. Okay, member 2. So we'll see the details for member number 2. Okay, member number 2, design moment M0 is found to be 264.6 M0. Alpha C is found to be 0.8, alpha C medium 0.23. Okay, 0.23. Now we want to find the moments. The reference book gives the transverse distribution directly. Okay, over here you can see the longitudinal distribution also. Okay, so this moment is distributed longitudinally as shown over here. Okay, at support, midspan and support, right? Now this moment has to be transferred transversely. Over here in the reference book this has been shown directly. Okay, so in column strip negative moment is 129. Okay, negative moment at the interior joint of column strip is 128.99. okay, that is 129, right? Positive moment is found to be 55.6. okay, so positive moment at about the midspan of the column strip is 55.57. okay, that is 55.56. simple, this is 55.6. now for full middle strip, right? So over here from software we get the moments for the half middle strip. Okay, so moment for this half middle strip plus moment of this half middle strip will give you the total moment for the middle strip. Okay, so these two are identicals. Okay, whatever moment we get for this half middle strip has to multiply by 2. That will be your total moment for the full middle strip, right? So first we will see the negative moment. Okay, so negative moment for the interior joint of half middle strip is 21.5 into 2, that is equal to 43. Okay, so this is 43. Positive moment, right? So let us see. Positive moment total, positive moment at about the midspan of the half middle strip is 18.5 into 2, that is equal to 37. Okay, so that is 37. So this is how uh, the flat slab can be designed by direct design method using the software, and you can simply just uh, get the answers in a minute, right? The effective depth considered by the software is 150, and that considered in the reference example is 180. So the steel will be different from the reference book, okay, because the effective depth is different, right? Fine. Okay, now coming to the another type of slab, that is circular slab. Okay, so first we will take design of circular simply supported slab. Example 1.1, reinforced concrete volume 2 by Professor Dr. H. Sasser. Okay, so this follows the theory of plates. Okay, so in that we will have mt, that is radial bending moment, and m theta, that is circumferential bending moment, right? So MT is referred as MR in software, okay, and M theta is referred as MT in software, right? So for this, when you're using the formula of elastic, when you're using the elastic plate theory, okay, then the steel reinforcement, standard steel reinforcement detailing will be like this, okay. So we will check the results with the software. Okay, effective span given is 6.13, radius is 3.065, F5 is 415, FCK is 20, and factor load is 12. Okay, and circular simply supported slab we are going to take. Okay, so let us do the run the program for circular slab. Okay, simple. So for simply supported, the condition to be taken is 2. Okay, so we are just going to give one slab, one number of slabs. So write 1, press enter. Okay, please press enter. Diameter of the slab is, okay, 6.13. Okay, 6.13, press enter. Load on the slab is 12 kilonewton per meter square. Press enter. F5 is 415, FCK is 20, and the condition is 2. Press enter, right? Simple. Click OK and finish. Okay. You can see the output, right? This is the output. Okay. I have shown the screenshot of the output over here. Okay. We can compare. Okay. MT, that is radial moment. In my case, in the software it is MR. MT at age is 0. Okay, age means radius is 3.05, right? So at 3 it is 0.89, so at 3.065 it will be 0. Okay, and at center, okay, when radius is 0, MT is 21.14, right? So 21.14. Similarly, M theta at age is 14.09, that is at 3.065. So at 3 it is 14.39, at 3.065 it is 14.09, and at radius, when radius is equal to 0, then m theta is equal to, in my case it is mt, in the reference book it is m theta. This is 21.14, this is 21.14, right? Simple. Now if you want to solve this, many of the structural designer prefer to use circular isotropically reinforced slab. Okay, so in that case, the moment, midspan moment, central moment obtained from the yield line theory is given by this formula. So this is the moment. Isotropic reinforced slab means the diameter and the spacing of the reinforcement in both the direction is the same. Okay, so once you know this moment, you can use the graph which I saw you in the beginning and find the spacing, or you can use this formula and find the required area and spacing, right? Simple. Okay, now let us take the another example, example 1.2, that slab, circular slab with fixed edges. Okay, okay, effective span is 7.63, and the total factor load is 18. Okay, so let us run the program. Okay, circular slab 1, press enter. Diameter is 7.63, 7.63. Load is 18.4 kilonewton per meter square. Fi is 415, FCK is 20, and the condition is 1. Okay, for fixed, it is condition is 1. Okay, okay, right. Let us click finish. You can see the output, right? So this is the output. Okay, so this is the screenshot of the output. Okay, fine. So let us see m theta, mt at the edges. Okay, the radius is 3.815. Okay, so at 3.815, the mt is equal to 33.47. Okay, over here it is at 3.75, it is 31.78. So at 3.815, it will be 33.47, right? At center, when the radius is 0, it is 16.74. M theta at the outermost edge is 0. Okay, that is at 3.815. Okay, at 3.75 it is 0.75. So at 3.815 it will be 0, and at radius is equal to 0, at center it is 16.74. Okay, it is 16.74, right? So this is how you can do the design of the circular slab, and this shows the deflection of the circular slab at different points. Okay, so you can also use these formulas for fixed and support. This will give you the moment at the midspan, and this will give the moment at support. If you are doing the circular slab design as a circular isotropic reinforced slab. Okay, so this comes from the yield line. Okay, so these are the ultimate moments, and then you need to do the check for the serviceability. Okay, so this is how you can do the design of various slabs. Okay, by using the software, which can save a lot of time. Okay, so in practical field, you can have some another types of slabs also. Say you can have an equilateral triangle. Okay, so let us see this, go through this fast. Okay, let me select this option. Say the depth of the slab. Over here you have to use a tab enter key. Okay, so say the depth of the slab is 125, press enter. Effective cover is at 25, press enter. Fi is say 415, press enter. FCK is 20. Okay, now say suppose it is an restraint slab, and ASTX, positive ASTX is 300, negative ASTX is 300, positive ASTY is 300, and negative ASTY is also 300. Then we want to find the collapse load. Okay, 300, press enter, 300, press enter, 300, press enter, right? Now we have to give L, that is say 5 meters, right? Press enter. Okay, so the collapse load that this slab can carry is 72.75. Okay, you have to provide reinforcement in this and in this direction, right? Okay, say you had to design the hexagonal slab for the same details. Okay, you can click, then you can see that the collapse load is found to be 6.43. Okay, say this is L, this is 5 meters. Okay, in this case this is L, this is 5 meters, right? This is L, this is L, this is L, this is L. Say if it is an octagonal type of slab. Okay, then the collapse load that the slab can take is 3.34 for this details, right? So these are some non-typical slabs which can come in practical field. Okay, these are very common typical slabs which comes in practical field. One edge free and three edges simply supported. One edge free and three edges continuous or restrained. Two edge free and two edge continuous or fixed, you can say, right? Fine. So let us take condition one. See, our Fy is 415. Okay, over here you do press tab G, press tab. FCK is 20, press tab. So the design load is 8, press tab. LX is 5, LX is LY is 6, AST positive is say 300, ASTX positive per meter is 300, ASTY positive per meter is 300. As this is a simply supported slab, so we are assuming there is no negative steel, 0, 0, and the effective depth is say 100 mm, right? Let us calculate. Okay, so the ultimate or the collapse load with this slab can carry is 5.2. Our design load is 8. So either we will have to increase the slab or increase the steel. Okay. Similarly, for the same details, say I have a restraint slab, and so let me provide this as 300 mm. Okay, negative steel, right? And this also as 300 mm. Okay, now let me calculate. Okay, so this is 7.5 and the design load is 8, so you will have to either increase the depth or the steel. Okay, these are the collapse load. Say if you had to design this slab, then choose condition 3, calculate, then the collapse load that this slab can carry is 44.12 and this design load is 8, so which is not okay. So either you increase the depth of the slab or increase the steel. Of course these are all collapse load. Okay, and you definitely have to check for the serviceability, that is deflection and crack width. Okay, so this is how you can use a user friendly software for design the slabs, different types of various slabs which we just saw in this video. Okay, you can download the software MMS program from the website mmsprogramcivil.com. Please like, share and subscribe this video channel. I hope you must have found this video useful. Thank you.